Hello, I'm Dr. Huy Nguyen. You can call me Professor Amin. Today we will go through Chapter 1 and review some important organic-related concepts in general chemistry. The first question is, what is organic chemistry? It is a study of carbon-containing molecules and their reactions. Later we will learn how to draw organic molecule structures using different representations. The second question is, why organic chemistry matters? Historically, organic molecules come from natural sources. People believe that there is a vital force that only living organisms can make organic compounds. When we go to grocery store, we see some organic food. Those foods are defined as a food produced through farming practices that only use natural substances, no artificial chemicals, such as pesticides or fertilizers. Now we believe that there is no difference between natural and synthetic organic chemicals, as long as they have the same structure. In theory, every chemical substance synthesized in nature can also be made in a chemical lab. Organic compounds are very important for living on Earth, as they are found to be present in all living organisms, in the forms of DNA, proteins, carbohydrates, lipids, and so on. They are the main ingredients in food, clothes, pharmaceuticals, plastics, polymers. And last but not least, it is important for you because you need to pass this course, and some of you needed to go to the medical school. After this course, you will become an organic chemist. As an organic chemist, what do we do? Some organic chemists are interested in making new molecules or finding a new way to make old molecules in a more efficient approach. This branch of organic chemistry is called synthetic chemistry. Some organic chemists focus on studying the mechanism of reaction, why, how, and when a reaction occurs. Others may be eluded by using organic compounds to make new materials, such as producing conducting material using polymer or creating LED screens. In Chem 211, we will mainly focus on understanding a chemical reaction mechanism. For example, how do I know that if I mix hydroxide with methyl iodide, a reaction occurs or not? You will see this reaction happens as a result of a bond formation between oxygen and the carbon, while carbon-iodine bond is broken. The bond formation and breaking are related to the movement of electrons. In this case, a pair of electrons from oxygen goes to carbon, while a pair of electrons in carbon-iodine bond transfer to iodine. So, electron will be our lover for this course. The smallest unit of a living organism is a cell. In chemistry, the smallest unit we consider for this course is an atom. An atom is composed of two parts, nucleus that has proton with positive charge and neutron which is neutral. The number of proton is called an atomic number, Z, and it determines the position of an element in the periodic table. The total mass of a neutron and protons are called atomic mass. Outside the nucleus are electrons rotating in a specific orbit. This model of atom is called the Bohr model of an atom, which treats the electrons as an individual particle. Electrons are located in different shells. With the development of quantum theory, scientists later discovered that electrons also behave like a wave. So instead of consider electron as a solid particle, electron is considered as a cloud of negative charge around the nucleus. The shape of the cloud depends on the energy level of the electron. and that and the cloud is defined as an orbital. The s orbital has a spherical shape, while the p orbital has a dumbbell shape. In the textbook, we draw an atomic orbital like this. Every two electrons share a cloud. If an atom has many electrons, they have many clouds around the nucleus. Think about we put all those clouds around the nucleus. And each cloud or orbital has different energy. For example, orbital 1s is at lowest energy and it is the most close to the nucleus. The second shell has 4 clouds, orbital 2s and 3 orbital p called 2py, 2px, and 2pz. The 3p orbitals have the same energy and we say that they are degenerate. Now, for example, if we have an oxygen atom which has 8 electrons, how do we put 8 electrons in those orbitals? This arrangement is called the electron configuration of atom, and it was developed by 3 scientists, Orbitals, Pauli, and Hunt. Orbitals said that we have to put electrons in orbital in order of increasing energy. The arrow direction in this diagram helps you to determine which orbital has a higher energy. For example, the first shell has 1s orbital called 1s. The second shell has 2 types of orbital, 1 orbital s and 3 orbital p, and so on. Pauli said that we can only put 2 electrons in an orbital, and they must have opposite spin. That means the spin up and spin down. Hunt said that when they are degenerate orbitals, 1 electron is added to each with their spins parallel until all are half full. Then the second electron with opposite spin is added to each degenerate orbital. So let's practice with oxygen atom. For example, oxygen has atomic number of 8. That means it has 8 protons and therefore 8 electrons. We will first put 2 electrons in the 1s orbital. The next 2s orbital is occupied with another pair of electrons. And now we have 4 electrons left. We have to put 3 electrons in each degenerate orbital first to make it half full, and the last electron will be added to one of these orbitals. It doesn't matter, with the opposite spin. So let's practice with other items. The first step is to draw a blank orbital. Follow this order: 1s, 2s, 2p, 3s, 3p. Second, we put electron follow 3 principles. So let's apply with carbon. Carbon is in the box number 6 of the periodic table. That means it has 6 protons and therefore 6 electrons. So we fill first orbital, second orbital, and now we have a 2 electron left. We have to put it in the 2p orbital. So the next item is sodium. Sodium has 11 electrons. So we put them in the inner orbital first. So now we have 7. That means 4 electrons left. We have to put another set of electrons. Now we have 10 electrons. So 1 left will be put in 3s orbital. What about chlorine? 17, the same. Build inner orbital first. Each of these So it is 10, it is 12, it is 15, 16, 17. So we can have a short form of configuration, like for the carbon 1s2 to s2 to p2, and for sodium is 1s2 to s2 to p6 3s1, and for chlorine it should be 1s2 to s2 to p6 3s2 and 3p5. So look at the atomic orbital of the carbon. The outer shell of carbon is the shell number 2, and it has a 4 electron overall. We say that carbon has a 4 valent electrons. So the valence electrons is the total number of electrons in the most outer shell. So what is the valent electron for the sodium? So the outer shell is 3, and it has only 1 electron. So sodium has 1 valent electrons. Similarly for chlorine, it has overall of 7 valence electrons. So if we look at the group number on the periodic table, the group number means the number of valence electrons. For example, nitrogen is in the group 5 because it has 5 valent electrons if you count all of them. Neon is in group 8 because it has 8 valence electrons. So 8 valence electrons. The octet rule said that an atom tries to have 8 valence electrons to fulfill all of the orbital of the outermost shell, so as to become very stable noble gas. For example, nitrogen in group 5. So it needs 3 more electrons to become a noble gas. So in any chemical reaction, nitrogen will tend to gain 3 electrons to become an atom that has an electron configuration like the most noble gas, the most close noble gas to nitrogen, that means neon. So we see that the electron configuration of nitrogen is very similar to neon in this case. And also we know that the number of electrons determines the reactivity of an atom, because noble gas fulfill electrons in all orbitals. They do not want to give away or gain more electrons. Therefore, it is very stable or inert. That's why we call it the inert gas as well.